So we have a little spring-loaded gun shooting a little suction cup dart straight up. So inside of this gun here, there's a spring. And then, of course, you compress the spring, you pull the trigger, and the dart will fire straight up. So let's say the dart goes 5.8 meters straight up. Let's say it's a 0.16 kilogram dart. And let's say the little spring inside of here was, we'll say it was compressed. Oh, let's go with 4.5 centimeters. So that's how far the spring was squished before it released the dart. We're going to find out a couple things about the situation. Let's find out, first of all, what is the K value of the spring, as well as how fast was the dart going when it actually was initially released in the situation. So to solve this question, it's all about energies. We're using energies for this question. And let's just look at kind of energies we actually have going on. Now, of course, in the gun, when we start, this is all, there's elastic potential energy. And then it shoots the dart. And that turns into kinetic energy when the dart is initially fired. And then, of course, as the dart moves higher up, it changes into gravitational potential energy. Okay, so we basically have three main energies. We've got the elastic energy it starts within the spring. That changes to kinetic energy as soon as it shoots. And as it goes higher and higher and higher, that kinetic energy is going to change into potential energy. Now we just use conservation of momentum, conservation of energy in this, where we have different energies at different places, but we're not going to worry about friction or anything like that. All those energies have to be the same. Things have to be conserved. So I'm going to go where I can actually find an energy. I can't find my elastic energy. I can't find my kinetic, but I can find my gravitational potential energy. So I'm going to start with that. If I do my MGH, I know the mass of the dart. I know it's a really heavy dart at 0.16 kilograms, but that's okay. I know my gravitational acceleration, and I know how high up it goes. If I do my MGH for that, we've got 9.1 joules of potential energy. Now, it's all gravitational potential energy at the top. That's the only energy we have up there. So that must be the total energy there, which means it's also the total energy everywhere else. So that 9.1 joules, first of all, must have come from the spring in the first place. And it was also turned into kinetic energy when we fired the the dart. So we can take that total energy and we can put it wherever we need to and solve for individual things. So the first thing I'm going to do is I'm going to take it, let's move it down one notch into the kinetic energy. That 9.1 joules of gravitational potential energy must have also been how much kinetic energy I started with. So if I take that 9.1 joules and I make that equal to the kinetic energy of the dart, I can solve for how fast the dart must have been going when it was initially fired. So I got the 9.1 joules, I know the mass of the dart, and we'll rearrange, and we should get around 10.7 meters per second. Okay, now do the exact same type of thing for the very bottom of the situation where it's in the spring. And that's where all the energy is, that 9.1 joules, it came from the spring in the first place. So my elastic energy, my elastic potential energy down there also was 9.1 joules. And this, of course, is equal to 1/2 kx squared. I've got the 9.1 joules, got the 1/2. K is what I'm looking for. I've got my X value. That my X value is the 4.5 centimeters. Just make sure that you actually change that into meters, and don't forget to square root it or square it when you calculate it. So we rearrange, and if we solve for the K value, we should get around 9,000 newtons per meter. Okay, which seems really, really high, but keep in mind that's how much force would be required to squish this thing an entire meter, not just the 4.5 centimeters. So there we go. We just used conservation of energy, found the total energy in the one place that we could, and then just moved it where we needed that total energy to actually be, kinetic or potential. And you could take that 9.1 joules and put it anywhere in the situation you wanted, and it wouldn't make any difference. You could find individual potentials and kinetics through the entire path if you wanted to. You could also take that 9.1 joules. That's how much work was actually done to actually compress the spring in the first place when the dart was put into the gun. Once you have the total energy, it's kind of nice because you can use it in any way that you need to. Okay, that is that question right there. So let's try another question. So here's another really, really common kind of toy. Here we got a little Hot Wheels type launcher with a car in it, and then it goes down the track and goes off a ramp. So the car would, get fired out of here, and it would go something like this and something like that. And hopefully it lands on the wheels and keeps on going. Okay. Now, basic structure inside of the little tiny thing is there's actually a little spring in here. Well, it's usually a spring or elastic bands. And you sort of pull it back, it locks into place, then you press the button to actually fire it out. So you got a little tiny spring in there, you pull it back, you stretch it, and then you press the button, shoot the car goes flying out and goes over the ramp. Okay, so what we're going to do is we'll use, once again, the conservation of energy type ideas, try to combine a couple different kinds, and the conservation of energy, and see if we can find out a few different things. Okay, so let's get some values going here. Let's suppose, let's say this was, let's say this little spring in there. We'll say there's a spring in there. Let's say it was stretched out 5 centimeters. And let's get the K value this time. Say the K value was 250 newtons per meter, which is about right for a Hot Wheels spring thing. And let's say the little car in there, let's say that's a 35 gram car, which is about right for a lot of Hot Wheels types cars. So it's going to go flying along. It's going to jump up. Let's say it goes 20 centimeters into the air. Okay, and let's see if we can find out how fast it is going at the very, very top of the path. Now, this is all energies once again. So we're just going to follow about finding energies and different kinds of energies. All right, so if we go to the beginning part, way down here in the launcher, of course, this is all right here. This would be all elastic. This would be all elastic potential energy inside of here. Then, of course, it fires out right here. It would actually be all kinetic energy. And then it does, goes off the ramp and jumps up. And of course, up here, we've got both potential energy and kinetic energy because it's raised off the ground. So it's got gravitational, I'll add the gravitational. It's got gravitational potential energy because it's off the ground, but also has kinetic energy because it is moving, okay? And it doesn't matter where you would go in the situation. We're not going to worry about losing energy to friction or anything like that. All the energies are going to be the same. So the elastic energy we start with, the kinetic energy it has here, as well as the combination up there, all of those are going to be the same. So if I look at what information I have and where I can find an energy, the best place to start would be actually in the elastic because I got the K value, I have the X value, I can find out how much potential energy I started with in the actual elastic. So I'm going to start over there. So if I find my elastic potential energy, which of course equal to 1/2 kx squared, I can find how much energy I start with in the situation. All right, so I got the 1/2 kx squared, got the 1/2, got the k value, there it is. Got the x value, make sure you change that into meters, and I get 0.3125 joules. So there is my elastic energy I'm starting with. Now that'll be my total energy for everything, for the entire situation. No matter where I go, my total energy is not going to change. I start with 0.3125 joules of elastic energy, and I can put that anywhere in the situation if I wanted to. I could take that and I could go over here, and I can make all of that equal to kinetic energy, and then I could use that to find out, hey, how fast was it going when it came out, or what was the initial speed, or something like that. I could do that. But right now I'm concerned more with the speed at the top. So again, this would be for like the initial speed. But I can also then take that energy, and I can take it and I can move it up here. Now the only thing is, it's not just kinetic energy up there, it's both gravitational potential and kinetic energy. I've got both up there, okay? So if I want to find out how fast it's going, I got to target that kinetic energy, but I can't find it directly. First, since I know how high the car is going, I can find out how much gravitational potential energy it has. So that's what I'm going to do first. I'm going to find out how much gravitational potential energy I have up there. So up here, the car's got potential energy equal to mgh. Okay, so if I do that, I got the mass of the car, make sure you change it into kilograms. I've got the G value, I've got the height of 20 centimeters, make sure you put that into meters. If I calculate that, I've got 0.069 joules of gravitational potential energy. Okay, so now let's piece things together. I know my total energy is going to be the 0.3125. Okay, I know that's how much the total energy is going to be, and that's not going to change. I know at the top of the path up there that 0.069 of that is gravitational potential energy, okay? Which means whatever's left has to be the kinetic energy at the top of the jump, okay? So the kinetic energy at the top has to be the difference between the two. So with 0.3125, take away the 0.069, which leaves us with 0.244 joules of kinetic energy at the top of the loop. So that is how much kinetic energy I have. And of course, those two put together, once again, they would combine and give me my 0.3125 joules. So my total energy won't change. Okay. Now again, if we brought in friction and other stuff, that would be a little bit different, but we're not going to worry about that. So now that I know the kinetic energy at the top, I can make that equal to 1/2 mv squared, and that would be the speed at the top. I've got my 0.244 joules of kinetic energy. I've got the mass of the car. I can then calculate the speed. And if we do that, I get a speed at the top of around 3.7 meters per second. So that's how fast the car would be going at the top of the jump. So there we go. So once again, it's all about just finding an energy, hopefully a total energy somewhere, and then just putting it at different places and making sure the individual energies add up to that amount, and then solving for whatever individual pieces that you need.